In this video, we're going to be looking at section 4.3, which is all about quadratic functions and their properties. So just as a reminder, in the prior two sections, we looked at linear functions. In 4.1, we looked at linear functions very specifically. We talked about slope, y-intercept. And then in 4.2, we talked about linearly related data. Talked about finding lines of best fit for data that looked roughly linear. In 4.3, we're going to be talking about quadratic functions. Right? So if chapter 3 was the introduction to functions, and we talked about functions in general, domain and range, graphs of functions, where they increase, decrease, max and min values. In chapter 4, we're talking specifically about two specific types, right? Talking about linear functions in 4.1 and 4.2, and then in 4.3 and 4.4, we're going to talk about quadratic functions. We're just drilling down and being a little bit more specific and detailed here. One real obvious application of quadratics is what we call projectile motion. If we throw a baseball, if we shoot a cannonball at a pirate ship, right? We're protecting our castle. We see pirates coming. We shoot a cannonball. Anything where gravity is affecting the path of a particle, it is going to travel along the path of a parabola. And these general problems are categorized into the topic we call projectile motion. We'll look at a couple of these at the end of the section. So first thing we always typically do, see this in every algebra textbook, is the equation, right? The standard form of a quadratic function or parabola. So we typically write the equation as like y equals ax squared plus bx plus c. Right? Of course, we're using the f of x symbol in this section because we're talking about functions, right? A, b, and c are just real valued numbers. So these are what we sometimes call the coefficients, right? So this could be, 5 times x squared, 3 times x, plus 7. Right? So A, B, and C are just generic forms of real valued coefficients. So just a kind of reminder from the prior section. So remember back in 3.5 we talked about the standard square function, y equals x squared. Now we talked about if we multiply the square function by a number that's positive, it's going to stretch the equation vertically. So quick, rough reminder here, right? So if the coefficient is 1, we get our standard graph here in blue. Here's y equals x squared, our standard square function. If we multiply by a number smaller than 1, but still positive, that's a vertical compression, right? So here's my compressed graph, right, pushed down on vertically. And then if we multiply a number bigger than 1, that stretches the square function, right, pulls it up vertically. Just a quick reminder of that in 3.5. And then if this coefficient in the front was negative, right, so if this coefficient in the front was negative, that reflected the graph over the x-axis. So we kind of got the square function upside down. All right, so we're going to utilize that kind of same knowledge in this section as well, just to remind ourselves of kind of like the shape of the parabola, this parabolic path, this projectile motion that we might be looking at. So some standard things we're going to notice with parabolas, right? Parabolas are always going to have some symmetry, right? So we're going to notice this line of symmetry. This book calls it the axis of symmetry, right? The lowest point, which we sometimes call the turning point, right? So if we're kind of following along the path of this parabola, it decreases, it hits this lowest point, our local minimum, that we talked about in 3.5 as well, and then it changes direction and increases. So we decrease into and increase out of this turning point, this local minimum. And for a parabola, we call that the vertex. And then, here's a parabola that opens downward, right? So we're going to increase up into the vertex, and then we're going to decrease out of the vertex. And again, this is the local maximum that we called in 3.5. And again, for a parabola, we have this line of symmetry, this axis of symmetry for the graph. And again, obviously, just like we talked about in the prior example, if the leading coefficient here is positive, the graph is going to open up, and we're going to have this local minimum at the vertex. And if the leading coefficient is negative, like negative 3 times x squared or negative half times x squared, the parabola is going to open downward, and that vertex is going to be a maximum. Right? So that's just kind of all, we're just kind of summarizing this prior knowledge and putting it into the context of this new section on quadratic functions. All right, now also remember in 3.5, when we graphed square functions, we shifted them. We use what we call the rules of transformations, rules of shifting. And the problem with the parabola given in this form, let me go back, problem with the parabola given in this form is I can't really use the rules of shifting. So the first thing we're going to do in this section is we're going to convert this equation so that we can shift the graph. So to use prior knowledge that we did in 3.5, right, how would we convert the equation? And basically what we're going to do is use a technique called completing the square. So what I want to do is a quick reminder of what completing the square is, right? So back in probably an intermediate algebra course, you solved equations by completing the square. And just a quick review here. Remember that if I have this expression here, x squared plus 4x, and I want to complete the square, what I'm going to do is add the number 4 to here. So if I add 4, I'm going to get x squared plus 4x plus 4, and that factors as x plus 2 times x plus 2. Now that's what we call a perfect square trinomial. This factors as x plus 2 times x plus 2, which is x plus 2 squared. So the rule that we see down here is what we're really going to do is we're going to take the leading we're going to take the coefficient of the x term. We're going to take half of that number and square it. So we're going to take half of that coefficient and we're going to square it. And that makes the term a perfect trinomial, and then we could factor it. So if we come back, up to this example here, we take half of 12, which is 6, and then we square that, that's 36, and that's what we're going to need to add so that it factors nicely. So x squared plus 12x plus 36, this factors as x plus 6 times x plus 6. And if we take x squared minus 6x, right, I'm going to take half of negative 6, which is negative 3, and I'm going to square that, and that's 9. So I'm going to take 9 and add it, and that's going to make this a perfect square. X squared minus 3x plus 9 will factor as x minus 3 times x minus 3, which we write as x minus 3 squared. And then one quick reminder here with a fraction, right? So if this is the number 1 in front of the x, I take half of 1, which is 1/2. I square that, I get 1/4. So I'm adding 1/4, and this factors as x plus 1/2 squared. So something I want to show you the pattern here, all right? The factoring is really obvious, all right? So I take half of 4, square it, and that's the number that sits inside the parenthesis, half of 4. Right? I take half of 12 and square it, and I got the 36. But half of 12, which is 6, right, the number before I square it, is what sits inside this factored form. Right? So cool little trick there. Half of 6 is negative 3. Negative 3 squared is 9. So that's what I add. But that half of negative 6 is what sits here in the factored form. Right? Half of 1 is 1/2, and that's what sits in this factored form. So you can see that's the formula we get here, right? We're going to add, we're going to take the coefficient of x, we're going to take half and square it, and that's what we add to the trinomial, and that's the factored form. So let's take a look at a couple more examples here real quick. So let's suppose this is really like back in chapter 2. Back in chapter 2, you might have solved this quadratic equation by completing the square. So here's how we would have done that. We would have kind of grouped the x squared and x variables together. And then we're going to take half of this number and square it. Now, actually, before we take half of this and square it, what we need to do is we need to get this coefficient to be 1. So the square, the x squared coefficient has to be 1. So I'm going to divide everything by 2. I'm going to divide by 2, and that becomes 1. I'm going to divide by 2, and that becomes 3. And here's what I did. I took the 5, added it to the other side, and then divided by 2. So that's that line there. All right, now that this coefficient is positive 1, I can take half of 3 and square it. And that's what I'm going to do on the next line. So I'm going to take half of 3 and square it. And I have a typo here. I apologize for that. So in your notes, ignore that 36. Right? Obviously, that should just be a 3. So I'm going to take half of 3 and square it. So here's half of 3. Again, I'm going to square it. Now remember, if I'm solving an equation, right, this is solving an equation. If I add this number to the left-hand side of the equation, I also have to add it to the right-hand side of the equation. All right? So again, this is kind of a review of chapter 2, and I'm taking half of 3 and squaring that. That's going to complete the square for me, right? So I just showed that this would be 9/4, right? Nope, and I fixed my typo there, I guess. So I just showed that this would be 9/4, and then when I add the 9/4 to the other side, I'm going to get a common denominator between these two terms, right? So the common denominator would be 4. I'm going to multiply by 2 here, multiply by 2 here, and that's going to become 10/4. So now I have a common denominator on the right-hand side. So on the left-hand side, I have a perfect square trinomial. And remember our trick. Our trick is that it's going to factor into x plus and this number before it got squared. So x plus that number, right? X plus that number, right? And this becomes 19/4. So over here, I wrote x plus 3 quantity squared equals 19/4. Now, back in chapter 2, what we were doing was we were solving this equation for x. So to finish this off, right, I'm done with the completing the square piece, but to finish this off, I'm going to get rid of the square by square rooting it. So I'm going to square root the left-hand side, square root the right-hand side, and I'm going to get x plus 3/2 equals, and then add plus or minus the square root of 19/4. And then I'm going to subtract this to the other side. So I'm going to negative 3/2 plus or minus. And then square root of 19 in the numerator is square root of 19. And then square root of 4 in the denominator is 2. And so there's my two answers. I got negative 3/2 plus root 19 over 2 and negative 3/2 minus root 19 over 2. All right, so back in chapter 2, we would have solved a quadratic equation by completing the square, right? And that would have been one technique we would have learned. Now, I want to bring up some technology and check my work. All right, so if I bring up Wolfram Alpha and I type in, solve 2x squared plus 6x minus 5 equals 0. Remember, that was my original equation, 2x squared plus 6x minus 5 equals 0. And I type that in. Notice what it does. It gives me the two solutions that we found by hand, and then it even shows me graphically, right? This is a parabola, and I have in essence set y equal to 0 and found the x-intercepts of the parabola. So those are my two x-intercepts that I just found on that parabola. And so I kind of checked my work really nice there. Now, the whole reason that we're bringing completing the square up in this section is, remember, what we were wanting to do ultimately is graph the parabola by shifting. So if I have this parabola here in this next example, 2x squared plus 8x plus 5 equals 0, I can't really use my rules of shifting from back in chapter 3 and 3.5. So what we would have to do is complete the square. So I'm going to take the same approach, right? I'm going to group the x squared and the x variables, and I'm going to kind of leave the 5 to the outside. And then in order to complete the square, I need this coefficient to be 1. The coefficient of the x squared term has to be 1. So I'm going to factor out the 2 that exist between these guys. So I'm going to factor the 2 out, and that leaves me with x squared plus 4x inside the parentheses. Now that this coefficient of 1, I can take half of x coefficient and square it. So I'm going to take half of 4, which is 2, and then 2 squared is 4. So I'm going to add 4 inside the parenthesis. Now I got to keep the equation balanced. So what I technically added was 2 times 4. I added 8 on the right-hand side of the equation. So I would need to add 8 on the left-hand side, or just subtract it from the same side, the right-hand side. So that's what I did. I added 8 and then subtracted 8 on the same side of the equation. And then this is a perfect square. Right, that factors 2 times x plus 2 squared, and then 5 minus 8 is negative 3. Now, here's the idea in the section. This equation is the same as this equation, right? So this parabola, 2x squared plus 8x plus 5, is the same parabola as 2 times x plus 2 squared minus 3. All right, so just to show you that these two equations are the exact same parabola, right, I brought up my TI graphing calculator, and I could do this on Desmos as well, but I decided to do it on the TI. So in the y1 equation, I'm typing my original equation. Excuse me, in the y2 equation, I'm typing my new version after completing the square. And if I do a graph, let me do a zoom standard window. Here comes the y1, and then there's the y2. Did you see it? I don't know if you saw it. I know I definitely didn't see it. So let me do this real quick. Let me hit the y equals screen, and I'm going to arrow over to the left of the y1, and I'm going to arrow over to the left of the y2. And I'm going to change this graphing feature. I'm going to hit the enter button a couple times. I'm going to hit enter, and there's a thick line. I could leave it on that if I wanted, or I could hit enter. There's shades above the graph. This shade's below the graph. Here's what I really like is this feature. So it's like a little circle. So it's going to graph the equation with a circle, and it slows the graphing down. So check this out. If I go back to my Zoom standard, here comes my y1 graph, and then in just a second we're going to see y2 lie right on top of y1. So the two equations are identical. Even though they look different by completing the square, they are the same graph. Now what I could do is I could go to the table above the graph button. I can do second graph and go to the table, and I can see that for any value of x, y1 and y2 are equal. Right, for any value of x, y1 and y2 are equal to each other. So these two equations are the same. So that's actually a really cool way to check you're completing the square, is to graph them and see that they match each other. All right, so now that we have reviewed that concept of completing the square, right, here's what the book is going to want you to do, and My Math 5 is going to want you to do for the first couple homework problems. In order to graph this parabola, they're going to want you to complete the square and then use your rules of shifting. So remember what our rules of shifting said about this equation. This told me I was going to shift the graph to the left 2 units. This told me I was going to stretch it vertically by a factor of 2. This told me I was going to shift it down 3 units, right? So let's review that real quick. So let's suppose we were told to graph this equation, 2x squared plus 8x plus 5. So we complete the square on it, and we look at this graph in this new version, right? So remember, we start with the standard square function. This is what we did back in 3.5. And then the next thing we do is we multiply by a factor of 2. We stretch it vertically, right? And then we're going to shift it to the left 2 units by looking at the inside, right? Adding 2 inside the square. And then we're going to shift it down 3 units. So again, falling back on some prior knowledge here, point out to you that when this leading coefficient is positive, right, the parabola is opening upward. So we can see the parabola is opening upward, right? That's going to mean that this vertex is a local minimum when that happens. And again, I'm just pointing out to you that the horizontal shift left 2 units, right? The x-coordinate of the vertex here is the axis of symmetry. So this line of symmetry is always going to pass right through the vertex. All right, now the reality is we don't want to have to complete the square every single time we want to graph a quadratic function. That is really tedious and time consuming. So what we really want to do is create a shortcut for ourselves, and this slide shows you what that shortcut would be. So just point out to you right here, right, if we're going to complete the square on this equation, it's now going to look like this. And the formula that the book connects to you for is that the x-coordinate of the vertex right here, right, this h value, that's the x-coordinate of the vertex, that's always going to be given by this formula, negative b over 2a. So if we're given the parabola in this form, we don't want to have to complete the square. So the shortcut is going to be to take b, take the opposite of that number, and I'm going to take the opposite of the b, and then I'm going to divide by 2 times the a value. And that's always going to give me the x-coordinate of the vertex. That's what this is going to give me here, the x-coordinate of the vertex, right? And you can see down here in this box, they're kind of showing you the vertex as an ordered pair. Now, the other part of this shortcut is I don't want to have to memorize all of this. Here's the y-coordinate of the vertex. That's going to be a pain in the butt to memorize. So I'm just going to point out to you down what's kind of nice about this ordered pair representation. As they're pointing out to you, I'm going to take b over 2a. I'm going to take the opposite of that. And then I'm literally going to take whatever this number is. Suppose this value is 7. I'm going to plug 7 back into my equation and find the y value. So I'm going to find f at negative b over 2a, and that's going to give me the vertex. All right, so this next example is us wanting to find the vertex and the axis of symmetry, and determine whether the parabola opens up or down. And we don't want to have to complete the square, so we're going to use that prior slide as like our shortcut. So the first thing we're going to remind ourselves, right, the x-coordinate of the vertex is negative b over 2a. So that's the first thing that I'm going to find. So I'm going to point out to myself a is 2, b is negative 3, and c is positive 2. So if I use negative b over 2a for the x-coordinate of the vertex, I'm going to get 3/4 as the x-coordinate of the vertex. Right? Now I'm going to take 3/4 and I'm going to plug it back into the equation, and I'm going to find the y value of the vertex. So So if I do that, I get a y value of 7/8 for my vertex. All right, so as an ordered pair then, my vertex is the x of 3/4, the y of 7/8. Now also could look at this equation here, and because this leading coefficient a is positive, I know the parabola is going to open upward, right? So I could do a real quick rough sketch of the graph, right? Since I know the parabola opens upward, I could literally rough sketch the graph, plot the vertex of 3/4, 7/8, and then just sketch it opening up. Rough sketch of the graph. All right, there's my axis of symmetry, right here is my x-coordinate of my vertex, so there's my line of symmetry. I haven't found the y-intercept at all. I know I wasn't asked for that detail, right? I was just asked to find the vertex, axis of symmetry, determine if it opens down, and then I added that extra piece of information, sketching the rough graph of the parabola. Now something else I do want to point out to you here, notice that in this case this parabola has no x-intercepts. So if I were to set y equal to 0 and try to find the x-intercepts, I'm going to get imaginary numbers, right? There's going to be imaginary numbers. There's not any real x-intercepts, all right? So there's this problem of sketching a rough sketch of this parabola, finding the vertex axis of symmetry. All right, now speaking of those x-intercepts that I mentioned, there's also another concept in this section about x-intercepts in general, right? So if I have ax squared plus bx plus c equal to 0 and I'm finding x-intercepts, think of the three basic things that can happen. But if I'm using the quadratic formula, all right, the quadratic formula has under the radical the discriminant. Right, so again, I paused the video real quick and I just wrote out the quadratic formula. Remember, if you're solving the quadratic equation, right, if you have a quadratic equation, ax squared plus bx plus c, and you set it equal to 0, you're finding x-intercepts for that parabola. So if I'm finding x-intercepts for this parabola, the easiest thing to do is to use the quadratic formula here. Right, so the quadratic formula is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Now remember, this number under the radical can't be negative, right? I get square root of a negative, which is imaginary. So this third case that we see right here says if that number under the radical is negative, then the graph has no x-intercepts. And that was like we saw in that prior example. And then this summary kind of goes on to point out that if that number under the radical is positive, then we're going to get two x-intercepts. We're going to get two places where the graph crosses the x-axis, right? So that's number one here. And then number two says, well, if that term under the radical is equal to 0, and then the graph is only going to have one x-intercept, and that will be the vertex, right? So think about this. If this is equal to 0, right, then this is gone, and I, in essence, get negative b over 2a as my x-intercept, and that is my vertex. Right, and that's what you see in these three quick rough sketches here. Here's case one, right, the two x-intercepts. So if the term under that radical is positive, I'm going to get two x-intercepts, right? Here's where the vertex is the one x-intercept in both of those examples, right? And then just like the prior graph that we did, here's where we would have no x-intercepts. All right, so let's take a look at one last graphing example. So in this graphing example, we're going to add some more detail. So we're going to talk about the intercepts, x and y intercepts here. And then we're going to talk about domain and range. We're going to talk about increasing and decreasing. So the first thing I'm going to always do is find the vertex of the parabola, right? So I'm going to take negative of 6 over 2 times a, and that's going to give me 1 as the x-coordinate of my vertex. And then I'm going to plug 1 back into the equation, and I'm going to find the y-coordinate of the vertex. In this case, y equals 4. So once I determine the vertex, right, I'm going to look at that leading term of negative 3. I'm going to point out that the parabola opens downward. So I could rough sketch, plot the vertex, and plot the direction of the parabola. What we're going to do for letter A here is add some more detail. So we're going to find the x and y intercepts. So if I set y equal to 0, here's 0 equals negative 3x squared plus 6x plus 1. So I'm setting y equal to 0, and then I went ahead and just kind of added everything to the left-hand side and then use the quadratic formula. So you can notice right here is that discriminant b squared minus 4ac, and for this example that turns out to be positive 10, so we're going to get the 2x-intercept case here. Right? So I just went ahead and plugged in my calculator 1 minus 2 root 10 over 3 and 1 plus 2 root 10 over 3, just to get kind of a decimal number to kind of get a good feel for where those x-intercepts would fall. So if I were to plot those points, right, here's that graph. Here's my vertex of 1, 4. And I can see the graph is opening down, right? There's my axis of symmetry that goes right through the vertex, right? Here's my two x-intercepts, negative 0.15, 2.15, and then I can find the y-intercept pretty easily. If I just plug 0 in for x, that gives me y equals 1 as my y-intercept. So adding those intercepts gives me a little better detail on the sketch of the parabola. All right, so let's take a look at letter B. So now the rest of these questions really come from the graph. So we've really done all the work to answer B and C, right? If you think about this for a second, what's the domain and the range? Well, for the parabola, there's no place the parabola is going to be undefined. I never have division by 0, never have square roots of a negative in a parabola function. So quadratic's domain is all reals. And when I look at this graph in particular, I can see the graph doesn't go above y equals 4. So my range is going to be from 4 down to negative infinity, and of course we're going to write that chronologically from smallest to largest. So we're going to always say from negative infinity up to 4 is my range. And then for letter C, where the function's increasing, right? So here's where the function's increasing. And again, when we're looking for where functions are increasing, we're looking over the domain, right? So we're going to read the graph from left to right. We're going to say from negative infinity all the way up to x equals 1, the graph is increasing. And then we're going to say from 1 out to infinity on the domain, the graph is decreasing. Okay, so again, a reminder here that at the end of this section in the e-text, there's a nice little summary for the steps for graphing a quadratic, right? And they tell you in step 1 to complete the square, but remember, this is the first option. Right? And what we really want to do in this section, we don't want to have to complete the square and then use rules of transformation. So instead, we're going to just find the vertex from this general form here. And then once we know the vertex, that's my axis of symmetry. And then, once we know the value of A being positive or negative, we can sketch the graph opening up or down. We can add details of x-intercepts. Okay, so as always, don't forget that as you work on homework in my math lab, if you have questions, please post them on the discussion board, and I'll see you in the next video.